And welcome to 17.2, where we're going to be talking about measuring and expressing enthalpy changes. In this particular section, we're going to do exactly that. We're going to introduce you to the idea of calorimetry. We're going to talk about how we know how much energy gets transferred from one object to another. And then we're going to also talk about how we write out what are called thermal equations. Okay? So let's go ahead and get started. First of all, calorimetry. Calorimetry is simply the precise measurement of the flow of heat in and out of a system. All right. So the prefix calor is dealing with calories, our unit for heat. Metry deals with the measurement of, so we're simply measuring the calories. Now, thermochemistry as a whole is simply the study of the movement of heat, where calorimetry is the precise measurement of the amount of heat flow in and out of a system. And we do this measurement using calorimeters. I'm not going to write out a definition for a calorimeter, but there are basically two types. You have this one, which is actually called a coffee cup calorimeter. That's an E right there, calorimeter. And because it's typically used in the classroom, we just simply put two coffee cups together and do the reaction right in there. Because it's insulated and doesn't allow heat to escape, or at least it's very, very minimal. All right. You can get more fancy calorimeters. In fact, this one has a nice lid on it. We do have some of those as well. But basically, you're nesting foam objects so that heat cannot escape. If you used a glass or a metal object, then the heat would actually escape right through the object, and we don't want that. We want to keep all of the heat inside of it. We use these coffee cup calorimeters when we are going to be using or having reactions at a constant pressure. When the resulting reaction does not change the pressure, we can use these coffee cups. And in that case, the heat Q is referred to as enthalpy, which is given a symbol H. So enthalpy and heat are the same thing when you're dealing with constant pressure, and that's pretty much all we're going to be dealing with in here. So for our purposes, heat and enthalpy are the same thing. For all you future chemists and physicists and engineers, you're going to be encountering some things where technically speaking, the enthalpy is not the same as the heat, or exactly the same as just the heat. All right. You can also use what are called bomb calorimeters. That kind of sounds cool. Now, a bomb calorimeter is where you want to keep the volume the same. Constant volume. In some cases, when you have a chemical reaction, you're going to have gases that are released. And when you release those gases, it would actually expand or just simply leave the system. Well, we don't want that to happen. So you put it inside of a device that does not allow the gas to escape, and therefore keeps the volume the same, but the pressure would build up on the inside. You're still going to be measuring the temperature change using a thermometer. So in essence, you're doing the same thing, except you do have to take special precautions when you're dealing with things that release a gas, or you have to take extra steps to ensure that you can measure all of the heat change or the temperature change. All right, so you have these two different devices. We'll be using the coffee cup calorimeters in class. All right, so let's go ahead and give this a try and see if we can't measure some enthalpy changes. So sample problem 17.2 says when 30 mils of water containing 0.025 moles of hydrochloric acid at 20 degrees Celsius is added to 30 mils of water containing 0.025 moles of sodium hydroxide at 20 degrees Celsius, in a coffee cup calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules during this reaction if the highest temperature observed is 27 degrees Celsius. Assume the densities of the solution are 1 gram per milliliter. We also have to tell you that the specific heat is going to be 4.18 joules per gram per degree Celsius for the water. Alright, so in this case, if we want to measure the enthalpy change or the heat change, Q is going to equal Sm delta T. The specific heat is 4.18 joules per gram per degree Celsius. The mass of the system, well, this is going to take just a little bit of calculation, but it's easy. You have a total of 30 mils of water with the hydrochloric acid. You have 30 mils of water with the sodium hydroxide. So you have a total of 60 milliliters of solution, and we'll just assume that the volumes are additive. And the density of the solution is 1 gram per milliliter. So that means each milliliter weighs 1 gram, so therefore you have 60 grams of solution. Alright, so that's the mass. Delta T is the temperature change. Well, they both started at 20 degrees Celsius and it maxed out at 27 degrees Celsius. So you have 27 as your final. You had 20 degrees as your initial, and that would be your temperature change. So therefore, if you take your 4.18 times the 60 grams times the 7 degree temperature change, you have 1756 joules of energy. And they did ask it for in kilojoules, not in joules. So if you want to change this into kilojoules, you just got to divide by 1,000. 1 kilojoule is the same as 1,000 joules, or just simply move the decimal 3 to the left, and you'll get 1.756 kilojoules of energy. So that's how much energy was released when you mixed the HCl and the NaOH together. Alright, just to kind of give you an idea, if you were to draw a picture of this, let's go ahead and say here's our coffee cup. Okay, that's usually nested in another one. What you have is the water that the reaction is taking place in. So we'll go ahead and draw that water. You also have a thermometer in that water, like so. And you usually have a lid across these things, although sometimes we don't use the lid and we just simply measure it right away. You might lose a tiny bit of heat to the atmosphere. Okay? But what ends up happening is the HCl and the NaOH react. When that does, that releases heat. Well, that releases heat into the water, and so what you got is this temperature probe that's actually picking up the thermometer that's picking up the heat. Now here's the deal. This reaction is releasing heat, and so since it's releasing heat, Q actually has to be negative. So we're going to change these signs to a negative value because they are releasing heat. So that would be the appropriate way to measure or to express the enthalpy change, is to put that negative sign in there. Alright, so let's go ahead and try another one. A small pebble is heated and placed in a foam cup calorimeter containing 25 mils of water at 20 degrees Celsius. The water reaches a maximum temperature of 21.4 degrees Celsius. How many joules of heat were released by the pebble? Alright, now in this case, we'll go ahead and go back to our Q equals Sm delta T. The specific heat of the water, because that's actually what we're measuring, is 4.18 joules per gram per degree Celsius. The mass of the water is going to be, well, if it's 25 milliliters, the density of water is still 1 gram per milliliter. So 25 milliliters of water weighs 25 grams. Alright. The temperature change, it started at 20, it ended at 21.4, so therefore the temperature change is just 1.4 degrees Celsius. And so when you perform that calculation, 4.18 times 25 times 1.4, we get 146.3 joules of energy that was absorbed by the water and released by the pebble. Now, in this case, again, the heat is being released. However, the question says that it's being released, so we're not going to put the negative sign in there. If it says that it's released, you already are saying the direction of flow of the heat. In the previous example, it just said what is the enthalpy change, which is right here. Well, they're not saying if it's being absorbed or being released. So if they ask for a change, you have to put the appropriate sign in there. The negative sign means that it's released. It's an exothermic process. A positive sign means that it's being absorbed. It's an endothermic process. All right. One last note that's important here. We talked about the law of conservation of energy in 17.1. The whole reason why the entire reason why we can measure the enthalpy change of a system indirectly is because of this law of conservation of energy. Whatever energy is being released by, let's just say, the reaction is going to be absorbed by the water in the calorimeter. Whatever energy is being released by the water and going into a system, which was not the case here, is the same that's being absorbed. The law of conservation of energy holds. So therefore, we can measure the temperature change and calculate the energy change in the water or the calorimeter itself, and that would be the same energy change with the opposite sign that the system would be experiencing. That concludes 17.2.